Hello, and welcome back to A Slice of Physics. We're going to continue our discussion about Coulomb's law and discuss how we determine the force on a charge from two other charges. So we're interested in the net force on the charge from two charges. Here's our example question. It says that three charges that are 20 nanocoulombs each are arranged along a horizontal line. Charge B in the middle is 3 centimeters to the right of charge A and 5 centimeters to the left of charge C, and it's asking for the net force on charge B from the other two charges. Now, as in Physics 1, I will give you solution steps or recipes that you can follow for certain types of problem, and for electric forces and electric field problems, these are the steps we will use. We will first sketch the situation, and then we'd consider each pair separately. This is called the principle of superposition, where even though we're interested in finding the force on charge B from the other two charges, we're going to take one charge at a time. So we're going to determine the force on B from just A. Separately, we'll determine the force on B from just C, and then we will take the net of those two forces by adding them as vectors. So those are the steps we're going to follow. And so let's get started with that. I've got charge A over here, B 3 centimeters to the right of A, and C is 5 centimeters to the right of B. And each of these charges is minus 20 nanocoulombs. Okay, so that's our sketch. So step one is done. And now we want to consider each pair separately. So we want to look at the force of A on B. And here are the equations and constants we're going to need. So the magnitude of force of A on B is given by this equation as K times the absolute value of Q1, which in this case would be QA, times the absolute value of QB, divided by the distance between A and B, which I'll call RAB squared. And now when I put the values in, I get 9.0 times 10 to the 9 Newton meter squared per coulomb squared. And as before, we need to put the value of the charges in coulombs. So that'll be 20 times 10 to the minus 9 to convert the nanocoulomb to coulomb. And notice I've left the sign out because I only need the absolute value. That's QA. QB is the same value, 20 times 10 to the negative 9 coulomb. And all of that gets divided by the square of the distance, which was given as 3 centimeters, which I got to convert to meters so that it cancels the meters in the constant here. So 0.03 meters squared. And that gives us a value of 4.0 times 10 to the negative 3 Newton. Now this equation only gives us the magnitude of that force, and that's its value. And from the direction, we are interested in the force on B, and this is the force from A, and because A and B both are negatives, they will repel each other, so the force of A on B will be away from A, so to the right. So here's FA on B. Okay, so that completes this step over here, and now we want to determine the force on B from C. So I'll call that FC on B, and we would do it the same way. Constant times the absolute value of charge B times the absolute value of charge C divided by the distance between B and C squared, and that'll give us 9.0 times 10 to the 9 times 20 times 10 to the minus 9 times 20 times 10 to the minus 9. All our charges were 20 nanocoulombs. And in this case, the distance between B and C was 5 centimeters, which is 0.05 meters, and I got to square that. And when you solve that, you will get a value of 1.44 times 10 to the negative 3 Newton. Once again, that's only the magnitude. To get the direction, I got to go back here and see that, okay, I'm looking at the force on B from C. Again, they're both negative, so C is going to repel B, so the force would be away from C. So it'll be to the left. And since it's less than half of the previous force, I'm going to show a smaller arrow over here and label it FC on B. Now some of you might be looking at this and saying, wait a minute, why aren't these forces equal in magnitude and opposite in direction, because that's what we said were the pair of forces between two charges. Well, you're looking at apples and thinking of oranges. There is Newton's third law pair in each of these cases. So the force of A on B was the third law pair of B on A. And FB on A would be shown on charge A like this, repulsive because they are like charges. So this is FB on A. And that indeed is a third law pair to FA on B, equal in magnitude and opposite in direction. And similarly, FB on C would be repulsive, so it'll be to the right like this, FB on C, which is shown on charge C, which is indeed a Newton third law pair of FC on B. Those pairs do exist, but the forces of A on B and C on B are not Newton's third law pair of forces. Those are completely two separate things, so they don't have to be, in most cases won't be, equal in magnitude and opposite in direction. So that completes the second part of step 2, and now we are on to step 3, which is in order to determine the net force on charge B. I got two forces. I simply have to add them as vectors, as we did in Physics 1. To show that, I'm going to reproduce the diagram here at the bottom. So here's charge B, here's FA on B, and here's FC on B. And the sum of those two would be the net force on B. And I can do that in two ways. I can do it geometrically. So if I take the tip versus tail approach, I can take FC on B, drag its tail to the tip of A over here, FC on B, and then my net force would be from the original tail to the final tip. Or I could work with the numbers. I know that FA on B is 4.0 times 10 to the negative 3 Newton. And I'm going to call that as a positive value because it's acting to the right. And FC on B, I'm going to give it a negative value because it's acting to the left, and that's 1.44 times 10 to the negative 3 Newton. And so now that I have the directions captured in the sign, I can get F net as simply the vector sum of the two forces FA on B plus FC on B, which given our coordinate system here would be plus 4.0 times 10 to the negative 3 Newton. And to that I add a minus 1.44 times 10 to the negative 3 Newton. And that ends up being 2.56 times 10 to the negative 3 Newton. Or back down to our two significant digits, this would be simply 2.6 times 10 to the negative 3 Newton, which is a positive value. So this is acting to the right as shown here. In this slice of physics, we looked at how to use the principle of superposition to determine the net force on a charge from two other charges. We did that by considering each pair separately and identifying the force from each of the other charges on our charge of interest, and showing those forces as vectors on our charge of interest, and determining the net force as the vector addition of these two forces. And we also noted that the two forces shown on charge B in our example do not form Newton's third law pair, even though each of those forces does have a third law pair that acts on the other charges. Thanks for watching.